The topic for today's lesson is infinite geometric series. Last time we talked about finite geometric series. We didn't actually say that word, but we were adding up a finite number of terms, in this case the first three terms, and we had a fun little formula that could help us figure that out. And it required us to know what the first term was. It required us to know the common ratio and how many terms we're adding up. And when it's only three terms, it might just be faster to figure out the first three terms and add them up. The first term would be 2, half that, and half that. So both of these formulas should give us the answer of 3.5. Now technically they call that a partial sum of this sequence. It's only part of the sequence. It's only the first three terms. It's the third partial sum of this series. So what would it mean if we were adding up all the terms? Infinity terms. We would be adding up the first and the second and the third and the fourth and the fifth. And we would literally keep going forever. What does that even mean? This is that same series imagined in terms of area. So here I have the number 2 represented by filling up 2 of those square units. The number 1 fills up 1, a half fills up a half a square. And I just wanted to show you what happens when I try to combine all these together, combine all the areas together. So there's 2 plus 1 plus a half. And if you notice, every time I add another one, half of that remaining area gets filled up. So now that I'm adding this 1/8 of a unit, it's adding up half of that blank space. Here's the 16th. Here's the 32nd. And it's kind of starting to frustrate me because they're so tiny. But if I keep adding these little guys in, can you see that? I should be able to fill up the entire thing if I had enough pieces, but how many pieces would I need? I would need all of them because it's only going to fill up a half each time. So that's kind of a calculus related concept because we're sort of going towards infinity number of pieces. But if you notice, that total area winds up being how many of those squares? And it's looking like that sum is equal to 4. Let's try this fancy new formula that finds us the sum of all the terms. The infinite geometric series. The sum of all the terms should be the first term divided by 1 minus that multiplier, that common ratio. That should be equal to 2 divided by 1 minus a half is a half. 2 divided by half is 4, which matches that picture of those rectangles filling up 4 square units. Did you happen to notice the fine print in this formula? It was talking about how that common ratio has to be less than 1, or at least the absolute value does. It could be a negative number, but it has to be smaller than 1. And the reason for that is because when we have a common ratio that's smaller than 1, that means our terms are getting smaller. And that's the only way that little puzzle works, is if you're adding up smaller and smaller pieces as you go. So out of these 3 examples on this page, which one can we not use that formula on? And I'm kind of hoping you found this one, because on this one, r is equal to -2. Our multiplier is -2. What is that going to do to our terms if I plug in a 1 and a 2? So if I plug in a 1, and then I plug in a 2, and then I plug in a 3, and then a 4. This is one of those alternating geometric sequences. Well, if I try to add that up, those numbers are getting bigger and bigger. And even though some of these positive cancel some of these negative, it's still going to keep growing out of control because it's doubling every time. So they would say that this infinite sequence doesn't really have a sum. We're going to say that it has no sum. It's unbounded. It would wind up being infinity or whatever because it's never going to stop getting bigger and bigger, even with those negatives canceling some of it out. But these other 2 sequences, when we have a r value of 0.1 or a common ratio of 0.3, even if it was a negative 0.3. That's why the absolute value is in there. As long as it's less than 1, we should be able to find that infinite sum, that infinite series. So just practicing that formula a couple more times. We are going to find the first term, first of all. So we're going to be taking 3 times 0.1. So our first term would be 0.3. And then we're going to divide by 1 minus the common ratio, which is 1 minus 0.1. So really we've got 0.3 divided by 0.9, and that comes out as 0.3 repeating, which is actually 1/3, yeah? So we have a finite sum for the infinite series. Kind of mind-blowing. This next one, all we need is the first term. So 10 times 0.3 would be 3 over 1 minus the common ratio. 3 divided by 0.7. This comes out to a long decimal, but when I push my convert to fraction, it brings me back to 30 over 7, which that makes sense, right? 3 divided by 0.7. Yeah. So I'm going to leave it like that so I don't have to round anything. And then, like we said, this last one had no sum because it violated the rule that the common ratio has to be making the terms smaller. They can alternate, but they'd have to be getting smaller. Write the number 0.7 repeating as a fraction. This is actually an application of those infinite geometric series, and here's why. 0.7 repeating. If you're kind of smart about it, you could write that as 0.7 plus 0.07 plus 0.007. And each of these terms could just tack on another one of those 7s, if you know what I mean. And it would be an infinite sequence because those 7s go on forever. And when you look at this, can you tell that this is a geometric sequence? What is our multiplier? Remember, to figure out that common ratio, you could always take a term divided by the one that comes before it. 0.07 divided by 0.7 is 0.1. And so our common ratio here is 0.1. And that's going to keep working. 0.07 times 0.1 gets us an extra 0. And so maybe we can try to write this as the sum from the very first term to infinity. And what do we have? We've got our first term, 0.7. Our common ratio is that 0.1 to the I minus 1. Can you see how this is just a geometric sequence? So I'm just going to hit that formula that we learned. The formula goes, we're going to take the first term divided by 1 minus the common ratio. And in this case, we wind up getting, okay, if you type it in, it's going to say 0.7 repeating, but it actually winds up equaling 7/9. We'd have a 0.7 over a 0.9. If you multiply by 10 over 10, you get 7/9. So that's how we can show that 0.7 repeating is the same thing as 7/9. Kind of a fun application. This last little thing I wanted to show you is just a fun fact, but it's so fun I couldn't leave it out. Did you wonder where this formula for the infinite series came from? Here's the deal. When we're thinking about this, we're thinking about n here being infinity, right? We want to add up infinity terms. Well, if you take a number to the infinity power, and it's a number that's super duper small, like 1/2 to the infinity, 1/2 times 1/2 times 1/2 times 1/2. Type in as many as you can on your calculator. It turns out to be so small, it basically disappears into nothing. And if we disappear that r to the n into nothing, we just have 1 over 1 minus r. If you just stack that a1 up on top, that's where this formula comes from. Super neat. Just thought you needed to see that.